In this video, we will discuss how to deploy numerous interceptors to deter the impending asteroids. As we mentioned in the previous video, we could use Saturn V rockets to launch large nuclear warheads into asteroids. Saturn V's third stage and the Apollo spacecraft can be modified to be an asteroid interceptor with a nuclear warhead. By using all the fuel in the first stage and the second stage, and a portion of the third stage, the interceptor will be on the Lunar Transfer Orbit, LTO. The interceptor will ride the orbit to the other side of the moon. Once the interceptor has reached the other side of the moon, the interceptor can further accelerate to the asteroid for the intercepting mission. One issue with this is the Saturn V rockets were retired in the 1970s. Also, at present value, each rocket costs about $1.2 billion. As a comparison, the Nimitz-class carrier costs about $4.5 billion to build. In order to make sure at least 100 interceptors hit the target, we will have to launch 200 interceptors, which will cost us $240 billion, which is enough money to build 53 aircraft carriers. In addition, this cost estimate does not include the cost of the nuclear weapons. Time may be an issue as well. It takes several years to build one rocket, so we may not have enough time to design, build, and launch 200 rockets 10 years prior to the impact. We could start building them now, but we may not find a large asteroid for a while, so until we find an asteroid, we have to maintain 200 large rockets in good condition, which will also cost a lot of money. So why are rockets so expensive? In order to leave the Earth, rockets have to accelerate themselves to 11.2 kilometers per second, which is called the escape velocity. If the rocket goes slower than that, the rocket will be pulled back to the Earth. The fastest airplane, SR-71, flies about 1 kilometer per second, so rockets have to fly 11 times faster than the fastest airplane in history. Also, in the atmosphere, we cannot go but so fast, so rockets have to fly out of our atmosphere first, then we have to accelerate to the escape velocity. This requires very powerful rocket engines and a lot of expensive fuel. Alternatively, escaping the moon's gravity is not that difficult. If we launch interceptors from the moon, they need to accelerate only 2.4 kilometers per second to get out of both the moon's and the Earth's gravity. Also, since there is no atmosphere on the moon, interceptors can be accelerated on the surface of the moon, so that interceptors do not have to use their own fuel to accelerate to the escape velocity. We have material to build interceptors and the surface accelerator on the moon. The moon is abundant with iron, aluminum, and other minerals for construction. Once we build the surface accelerator, we can also use the same accelerator to send bulk material from the moon to the Earth's orbit. This concept for the lunar surface accelerator to launch material to space was a popular theory in the 1970s, and it was called the mass driver. It was never built, and one of the main reasons was the most important material for space operation was not available on the moon at that time. That important material was fuel for spacecraft. Therefore, we have developed a spacecraft engine which uses solid iron to produce thrust. The principle of this new engine is this. The engine electromagnetically accelerates solid iron to the speed of a bullet using the power from onboard solar panels or a nuclear reactor. The reaction of shooting solid iron is the thrust. It is Newton's third law, and all existing spacecraft engines use this law. So the moon can provide material to build interceptors and its fuel. The surface accelerator can launch the interceptors, and they can also send bulk materials and fuel for spacecraft back to the Earth's orbit. This space system could pay for itself, and it will defend our planet one day. Guardian Angel's project is about building this lunar electromagnetic interceptor launch system.